Okay. Compile time reflection. So this is talking about the shape of types within the source language itself to do metaprogramming and things like that. So let's switch this thingy here and get into it. So the main idea is to be able to summon a type schema enum for any type you have, and then do stuff with it. One example would be like a JSON serializer for any struct. You can generate that with the metaprogram at compile time using this. So let's make it work. What I think I've landed on is, so this is the core library, the prelude. So we have some intrinsic functions here. We have a function to get a type ID, which we'll eventually do a new type wrapper for. But for now, we'll just do U64. To get a type's name, this one's kind of standalone. It needs to fit in with the system. And then type schema, this is the big one. So interestingly, I've gone back and forth a number of times between this and this definition. But I think I like taking the ID because then this function can, well, you can still call it at runtime either way, but it allows me some more flexibility with how much of a tree I generate and a few other things. So for now, we're going to go with this one. But there's a very interesting problem that I was wondering about doing it this way. So we have no t. So this function can be called at runtime. And how do we know which type ID is going to be passed in? If we're calling this at runtime, then we must have baked in those schemas into the binary, like somewhere in static space. And the question is, like, did we just do all of them? And that's kind of what I thought you would have to do. But then I realized if someone passes in a type ID that they didn't receive from the type ID function, then it should panic. So all we have to do is bake in the schemas for every type for which someone calls type ID, which this is a compile time operation. The way to think of a generic is just a compile time function. So what we have here is, let me make sure my shot's okay. What we have here is a way to know every type that could be every type ID that could be passed a type schema. And then those are the ones we can bake in. So a type schema will actually just be a physical function, both in the LLVM backend and in the VM. So that's the plan. And then our recursive references will just be type IDs. I'm going to go ahead and call this type ID. It's hard to switch back and forth. Okay, so let's try to make this work. I made a little bit of progress already. So here is the type ID function, which is pretty simple. We just take our type ID and marshal it out into an integer literal expression, but we also get a type schema. We generate the type schema. This is get, but it also generates. So this ensures that it'll be in there, and then that's what we'll iterate over at backend we'll do like a big switch over all of the compile time schemas in order to, over all the type IDs we've seen in order to produce the schema. So really, a lot of the work goes into this backend. And if we go to get type schema, the idea is it produces a static value, which is exactly what it sounds like. It's my notion of a statically known value. And when you run comp time code, it actually produces one of these, sort of like a subset of every possible value you can have in a language, only like well-formed, finite kind of values. So you may notice there's pointer in here, but there's no arbitrary. There's only null pointer, because that's the only thing that I could reasonably then like transfer over to runtime and still know what it is, right? We can't transfer like an arbitrary memory address over. References you can do though, which I haven't put in here yet, but reference is really just like a degenerate case of what we're doing here in buffer. Anyway, so what we do with get type schema, and this is all happening in the type checker. So whatever work is done here is shared by both backends. And we're just building first we look up the built-in type schema. So what this is pointing to is this actual type definition, because this is what we're trying to build. Actually, we might be trying to build a type info. So I've been waffling back and forth between the two, but yeah, I mean, I think I'm just gonna get it working with schema, knowing that it's incomplete, because I guess you don't need your ID back out. And everywhere that I refer to a type, I'll put the ID in here. So technically, this should be good enough. Yeah, I'm not gonna worry about supplementing with the layout and stuff for now, even though it will be needed. So we're just gonna do type schema for now. It just means I won't be able to get the layout of, say, one of the fields of the buffer. But I could make analogs of size and align that take the type IDs as well, when powered by a similar mechanism. But anyway, back to this. So that's the schema for the thing that we're going to return. And then, there's that int kind enum in there. So I look him up, and I've got that in here as a type enum. And we just sort of switch on the type we were given, and make variant just produces a static enum value here, and just produce the thing. So here's the int variant. So I've implemented this far with my int type, so I think that we should test this. And in order to do that, we need to pick a backend. So we're going to test this with compile time running code, or test this in the LLVM backend. I thought the LLVM was more interesting. So if we come down here to type schema, what we have is here's the function. And so the way these internal functions work is the stub of the function is generated by the compiler normally, but then the implementation, because it's marked intern, the implementation is up to us. So our job here is to produce an LLVM body for the type schema function, which I can only think will be a giant switch over all of the known IDs, all of the IDs that the program should know about, and returning the schema for each of them. So I'm doing a fee and a switch here. And a fee node is a node that can return a different value based on where you branched from. So imagine a big fan out, and we're going to be in one of the arms based on what the type ID is. And then we're going to branch back to the return point, and based on where we come from, the fee is going to hold the value of the branch we came from. And this is a bit better than using like some stack memory to store the ID and doing stores in each branch, because presumably it's more of a directly analyzable, optimizable control flow type thing than munging around with memory. So that's why we do it. So I need the type schema type. So type schema type. And what we're going to do is we're going to code gen a type, because we need the LLVM type for this, K1 type. And which type are we going to code gen? Well, we need the type ID for type schema, this built-in function type schema, built-in type. And that's going to be in k1.types.builtins type schema. And we can unwrap that. And so that's a K1 LLVM type. So now what I want to do here is build a fee, and fee wants any basic type. So what we want here is, it's going to be type schema, which is going to be a struct, or an enum, which is an aggregate value for us. So what we want it represented as is its like canonical representation, which for us is actually going to be the LLVM type pointer. For reasons, it's just a lot better to point to structs by place than by value, and you're discouraged from using aggregate values for big values in like the LLVM front end guide. So what this will actually be is just the type PTR, I think. And that's okay. And so now let cases be a vector of int value, that'll be our type ID, and basic block. And then we're going to do a big old switch. So for each type in K1 schemas, this is the place where when we generate a schema, we update this map and put it in there. So we're going to iterate these in a random order because it's a hash map. It should be okay, not random. I wouldn't mind sorting it, but we can put in a little to do. My fingers don't work. Sort the schemas so we code gen more, not so much deterministically, but more predictably. And what do we do in each of these arms? So let's just slap a big old to do. This would be let my block builder block, not builder, so that would be module block. I think it's the context. Yep. the Inkwell API is interesting. So in our current insert function, yeah. And I just wonder, yeah, so we have a helper for this. So let's do that in the current function. So this is going to be arm type, and I wouldn't normally do this because generating these names is kind of expensive, but for us to see our LLVM code, we might as well do this. And this is going to be type ID as U32. I can borrow you if you want. Okay. Let me just shift a little so my mic can be even closer to my face, because apparently that helps. All right. And let's not put anything in there. We do need a type ID, so we'll do cases.push. The type ID needs to be an int value. So this is going to be as U32. So we need to get our LLVM type for U64. And I do have a thing called built-in types, but as you can see, I haven't put ones for the int widths because they're so easy. What I'll do is I'll actually just do ctx.i64 type because it's just right there. And then we're going to say from this i64 type, and this is the LLVM i64, we want a const int. So this is an int that we know at compile time, and then it wants a u64. So what we put in there is we're going to put our type ID as u32 as u64, and then sign extend is false because this is an unsigned value. So this i64 means I and u. It just means int. The signedness isn't in the type. The signedness for LLVM values is on the operations. So there's no signedness semantics attached to the value. It becomes signed or unsigned when you choose to treat it as such, when you, for example, like add, subtract, do another operation on the type. So we're going to push this case, and then this is just definitely going to be let type ID int value, and put him in there, and then this will be type ID int value, and then what we need is our block. So, and we have a big ol' to do. Yeah, that's fine. We're not doing anything yet, so this isn't going to work. And then our block, since we're doing a phi thing and switches can diverge, we need to make sure it converges back. So let's do that. And I'm wondering now if actually my microphone should just be near my monitor, because that's where I'm pointing my mouth. So let's try that. Okay. So the one thing we're going to do in my block, well, first we need to move the builder, position at end of my block, and we will build branch, and that will be an unconditional branch to the finish block, which we haven't created. Block, append basic block, finish, type schema finish, sure, and down here, wait, the fee, I forget where the fee goes. We want a reference to the fee early. So in the other places where I build a fee, we build it at the beginning. Yeah, we go to the end block, make the fee, and then we have the fee, and then we go back to our arm blocks. So let's do that. So we'll make the finish block, and we'll position in the finish block. So now our builder is at the end of our match, and we make a fee. Yep, now we instantiate our cases. The switch needs to go in the start block. So we need an entry block. We don't need to create one for this, but we do need to take note of it. And then the switch needs to be generated there, but we can't generate it until we've built our cases, which require knowing what the fee is. So we kind of have to build this thing inside out, I think. We're gonna add go ahead and add the incoming here. Oh, okay, we could do it at the end, but I kind of like doing it this way. So otherwise we'd have to make a vec of the incomings. Rather just store them in the fee. So it's the basic value and the basic block. We need the actual schema value. So this will be the schema value, reference to it, and the basic block we're coming from, which is my block. And then the branch to finish block. Okay. The schema value is, we have it here, static value ID. So cogen static value, which takes a static value and gives us a basic value, you know. No way. Okay. We need an else block. Our else block can also be our finish block. I don't really care. But the fee won't have an incoming for it. So maybe we just make a block where we trap. Okay, so that's taking out of our entry block. Else block. Append. Fail block. We'll call it fail. Miss. Let's insert something into it. let's make an unreachable. Well, I guess we should make a panic crash. Do I ever properly call crash? No. Okay, I mean, to do proper panic, proper crash. But we can go in here and we'll just build a trap. That'll trap, and that's okay. Now we make the finish block, we go to it, we make the fee, and now we got to go back to our entry block. To make our switch, and the switch. Oh my goodness, no. Doesn't matter where we go here. And that needs to be unwrapped. And now, finally, we can build our switch and pass in our cases. Okay, and we don't really need the switch. And now let's position in the finish block, which has the fee in it. And we need to produce an instruction value. So this would be okay. Fee. No, it's not even. Feed out as instruction. Did I do it? Wow. No way that's going to work the first time. I was thinking about deriving a default for this boy. Okay. Should we try it? So let's go to our example program. I had type reflection. I was trying, but there's like too much going on in here. So let's just take this down. Still doing that. That's just a point, so that's not gonna mess us up. You can't do this anymore. You have to call them twice, which is frustrating. But for now, I can do this. I can do fun get type schema for T of type schema. And what does that do? Well, that calls type schema with type ID T. Okay. Yeah. So that's pretty cool. I mean, I don't know. It's not all that often that you can get a real correct compiler error from your own language in LSP and then add an import and fix it. Just kind of makes me happy. So we'll update all of these to call get type schema. And I did implement unit and the integers. And this, we're just not going to compile. And what we will do now is run that file, which is called type-refl. And the compiler panics at internal compiler error, type schema on param 13966. Shoot. That's this, which is really bad. And I know why. So we're here in the type checker at compile time, and we're type checking this. We're not specializing it yet. And you call type ID on T. Which forces me to call type schema. So what I can do, it's not a concrete type. This type can't exist at runtime. What I can do is we can say if is function concrete. Let's look at his function concrete. So what we will do is we'll say self.types.get type variable counts. And what is the difference between that and get contained? Self.type variable counts.get. So what this is a helper data structure I store for every type that tells me how many inference holes it has in it and how many type params it has in it. And essentially, if it has any of them, then it's an abstract type. For every concrete type. Okay. Should we try it? Entered unreachable code. Operation type schema is handled in typer in the VM. Okay. Why? Test. Because we're running this statically. So let's not run it statically. Unexpected inline intrinsic type schema. It's not an inline intrinsic. Intrinsic operation is inline. Is inlined. So we had wrongly marked type ID as inlined. Well, it used to be. But now, no, type schema. Type schema is now a real function. Because it's doing that switch. And basic block and function schema. Does not have a terminator. Type schema finish. Right, because that's the end of the function. So I guess I kind of forgot that it might be our job. Right, so I was thinking I would just position back at the finish block and then let the rest of the code pick up, but this is actually a function that needs to... Wait, what's everyone else doing? Build unreachable, build return, build return, build return. No wonder we're returning an instruction value. Everything makes more sense now. Fee is not a basic value. Okay. Let's do some logging. Generating type schema, switch, arm for type, self k1, type ID to string. Found return instruction that returns non-void in function of void return type. Well, type schema should not have a void return type. So like allocate doesn't have a void return type. Intern fun alloc. What am I doing wrong? Oh, it's a struct return. Let me show you. So when we return a struct in LLVM, we actually pass in, we just store the result in an argument. We pass in memory, and the function puts the struct in there. So this is the parameter attribute. The pointer parameter specifies the address of a structure that is the return value of the function in the source program. This pointer must be guaranteed by the caller to be valid. SRET type argument specifies the in-memory type. So that's what that's about. Let's look, actually. I probably will have printed out fail. Type ref will fail. That's us. And fun... no. Define void type ruffle schema. Hello. Ooh. Oh, get type schema. This is the specialized one for unit. But as you can see, type schema itself returns void because it takes an SRET pointer and an ID. And then look. We switch on ID, and if we miss, we go unreachable. And we have no arms because we failed here. Maybe. If we failed in validation, though, that's something else. We have no arms. I guess we should be looking in type REFL to see. So I would not expect no arms. I would expect to have done type IDs for all of these. Ah, yes. No, it failed validation. So we need to figure out. This definitely isn't going to work until that's fixed. But for now, I guess what we can do. Oh, because our type ID. No. Anyway, our type ID is going to be in 1. Just to document why it's 1. That'll always be a pointer. sret putter, and we'll store. Shoot. So we got to return none. And instead we're going to store into sret putter our fee. And the fee into a value. We'll run. Found int value. Oh. Yeah. At 3166. But type schema I'm inspecting function argument. Function.parameter variables. This is different. Function physical params. So to get at the sret, do I know my function ID? I can get my function, the current insert function, and grab the first param. That might be the best thing to do. I definitely store the sret in a map. Yeah. Cogend function by function ID. Okay. So if there's an sret pointer, let's come in here. I have the function. Does it have its own ID? Yeah, no. It doesn't. It's okay, we only call this once. And we have it anyway. So now we go to the end and let sret putter cogend functions, LLVM functions, get function ID ramp, sret pointer, because we know that because this function returns a struct, we will have made one of those for it. And it's pretty neat, actually, that because I declare this, even though we implement it by hand, because we declare it in the source language, Think of all the code we don't have to write to generate the SRET by hand, because we're just using the compiler. Because up to signature, we do normal code gen. And then we're only replacing the body, right? Because it's intrinsic. It's kind of nice. Oops. All right. I don't know, type schema returns a struct, so we have to do SRET shenanigans. Type info not found. Indeed. It worked, but it exited with signal 5, which I think is a bad signal. So, no, that's a trap. We could debug it. I'm pretty sure it trapped. So let's take a look at the LLVM. So, optimized us all the way down to a trap. These friends too. Thank you. Oh, look at these. Get type schema. We have all our proper specializations though. These are all the types that we called it for. It's just that they're all collapsing down to an unreachable. Presumably, because this thing always turns into an unreachable. So what are we doing wrong? We capture our entry block. Yeah, let's debug so we don't optimize. That's gonna be way better. And then of course, if we run, we're gonna get a stick trap, which is fun. And breakpoint, right? Breakpoint and type schema, as expected. But now we can look at the code. And main calls type refl main, right? Type refl. Get type schema for each of these. So this is eventually going to become an unreachable. So why? We call SRET. No, all right. So we allocate a type schema on the stack. We call it with type ID 9, and that is the type ID of I64. And then we mem copy from SRET pointer to our SRET, from the call SRET into ours. And we copy 32 bytes, which presumably is the size of a type schema. I don't know how big it is. Okay. So then this must be trapping. This one. Oh, sure is. All right, yeah, there's nothing in here. So it's back to the fact that there were no branches. So we have type schemas. I'm not inserting. Ah! Let's go. Ah! Few node operands are not the same type as the result. Oh, shoot, that's hard to read. Why are they all 2? I think I might just need to look at it. Switch. Here's our switch. Switch ID. Oh, this is so neat. And those are all the types. Can we put a comment on these? I don't think you can. All right. And then all these do is branch to finish, as you do. And then the fee PTR, right. So the fee is of type PTR. Why is that? I told you it would be a pointer. But when I cogen static value, I think that we give back the struct itself. So let's try, what we're doing is an aggregate, the struct value for a struct. So for the enum, it's the actual struct value, because these things are like constants. But what we need from here to like interface with our runtime code that represents aggregate types as pointers is we need an address to it. And that's interesting because I think the best way to do that, we don't make a global, do we? No. We just do const named struct. So, because these are going to get reused so much, it might be better to have them in a global. Let's look at them actually. So each arm of the fee where's my fee? Oh, right. Oh, this is the wrong one. Type ref will fail. This is the fee with stuff in it. Look, these are globals. No, that's a type. And then the static value is just the tag. Any of them have payloads? Oh, it is the payload. This is the tag, int 012. So the third variant It should be the third variant of the enum and then the sixth variant of int kind. So if we go to built-in, what we should see is that int is third, first, second, third, and that I16 would be at index 5 of int kind. So 0, 1, 2, 3, 4, 5, and there's I16. So we correctly generated the value. The problem is we just need a pointer to this. So let's just put them on the stack. Let value adder or location, and I actually have a build alloca. This always bends my brain. Am I allocating space for a pointer on the stack? No, I'm allocating space for a type schema on the stack. Okay, so this is going to be type schema type dot rich value type. In the name, we're going to go with, ooh, shoot. We're having to do a store anyway. So what's the point of the fee? Is what I'm thinking, right? Because what this will do is actually make an alloca for each branch when they're all going to be of the same type. And if we need a stack pointer anyway, yeah, gosh, I wanted to use fee, but and you know what? We could even put it straight into the srep pointer. That's funny. That's funny. Then we're just less resilient to like a, to it not being sret. Okay, let's kill the fee, which means this code won't make sense anymore, and will make no sense to go to the finish block here. That's okay. Let me just directly use the srep pointer for now, okay? And then in each branch, we're just gonna store it right into the srep pointer. We don't have to go to it though. We don't have to position in it. Finish block can be, oh no, we do, because we're putting a return statement in it. Wait. Oh my goodness. We don't even need to know how much stack space to allocate because the caller already did it for the sret. That's kind of awesome. Element 1 of struct initializer doesn't match struct element type. I'm storing. Oh, this again. So the SRET is the type of the enum, but my value is a type of one of the variants, which has the same size and is compatible, but can't go in the same slot. And the way I get around this in other places is when I declare the global, I just use the variant type. So we need to do some pointer shenanigans, kind of. Struct initializer. Well, no, it doesn't matter. The pointer can be anything. Oh, maybe it does know the SRET pointer type. No, it's not going to type check a store. It's disagreeing about these two types, I think. Type schema.element 1 should be a tag. Oh, right. No. Element 1 of struct initializer. No, it has no issues with this value. It is to do with the store. But if I do my own alloca, will it not type check it? Unclear. That should... I don't know why I'm doing that. Unit. Oh, it is 0. The tag is 0. And then for this one, U8, the tag is 0. And it's this one, 2, I16, I85, the one we actually hand checked. So why? Core type schema int. I mean, I can't print. Would it even let me build this? When is this failing? Is that validation? Oh, it's the actual build command? Yeah. In the actual build command. So it validates the module and everything. And this is like a compiler error from Clang. So I16. The type is a struct of I8 and then an int kind. And then what I do is a value, int kind dot I16. So it wants I8 int kind. So we got to declare this thing of, oh, that's nasty. What was that note to myself that I had in this one? We actually have to specialize the LLVM struct type here because it won't allow an opt I64 with a sum. You have to cast it back to the struct type. Right. I make a new... Oh man, no. We build the type. Gross. I just don't do it for enum yet. Enum value. Const name struct. It's a problem with the value. Physical struct, which is of the variant. It's this value, which has the type of the variant. Shit. Because this is all static LLVM values, I can't just like bitcast them. Or can I? So what I'm saying here, the enum is typed as the variant. But then if something contains it, what it expects. And then to make things worse, actually, I'm not handling, I have this flag here for whether this is typed as the enum or typed as the variant. Because for typed as variant, what we're doing here is correct. But for typed as enum, we need to bitcast it back. Is that even possible? We could certainly... bitcast value type. Which has the same bit width. Which these kind of do. But you can't bitcast aggregates, I've tried. But I can't put these in pointers because we're doing just constant values. I would need to... Oh gosh. I need to make a type schema.int, which is this shape. And I produce an intKind.i16. This one's fixable because it doesn't have a payload. It's just the tag. But then, yeah, so I've done this code here. Okay. Specialize the LLVM struct type. I do each value. Type I produce is actually this would work fine. No, yeah, it has to be typed as the variant. Oh, if there's no payload. If I recurse this all the way up, it should just actually be okay because I'm still just gonna do a store. Yep. So we're doing the right thing for struct. For enum, someone's calling us and they're expecting an int kind. And we're giving them, based on this, an int kind .i16. And the way to fix that would be just to produce an int kind, since there's no payload. But what would be better is if they were expecting an int kind .i16. But I can't write that here. So what I have to do, instead of producing the variant struct type, I have to make a unique type for every static enum, just like I do for every static struct, by doing this, generating the values. Instead of calling const name struct here, I get the two values. I get the tag and the payload, and the payload's going to have a unique type based on what's inside of it. And then I make a struct from those, and I call const name struct on that type. So it's a bespoke type. So then what we'll be expecting here is not even going to have a name. It's just going to be this anonymous type that is, yeah. And what's funny is these types are completely compatible, but because of the name, I think, it doesn't like it. So what we would do is we would do like, so if it's none, then this is easy, because it will just be, oh no. So it'll be our job to, yeah, whoever calls us will just put whatever type we give back in. Our job is to do that instead of doing this. So the actual struct type is, it's variant. Basically, we have to do just for the payload what we do for every field up here. It's the LLVM type, tag type, struct type. Feel me? It's this, and then whatever the payload value, get type. Okay. Which we just have to trust that it's going to be the right size, that everything works, right? We could do an assert. That we can get alignment, but we can't get the size. Self.size info of struct type. It should be the same. right? Hopefully that works. So now what I return oh, nope. No, it's going to be, this is going to work fine because it's going to be the correct type. That's this. No, that's this case, I guess. Yeah. And instead of physical struct, we'll do our unique struct type. We'll make one there. Oh, goodness. We have to construct a unique type for this value. Because why do we have to do this? Because if we use the variant struct, the payload will come back with a more specific type than it. Since everything is represented as its most specific concrete types, specifically enum values in here, in this static world. Okay, kind of gross, and a gross comment, but I tried. It validated. This is good, and it compiled. Holy shit. Can I run it? It succeeded. Can I break at main and run it line by line? That's not what I wanted. So now I need to like go into, yeah, you're gonna link to that main. And you go like, do I need to go inside? And you go inside there? Yes. Okay. Why'd you go backwards? Wonderful. Love those debug spans. Something in here is using a span from the wrong spot. You ever seen the debugger go forward and back? It's okay, we're making progress. And we're done. Wow. Are you serious? Here's type schema. We switch on every type that you've talked about at compile time. And in each of these arms, we store. So here's what I16 ended up being. We're storing, and see how it's not named this time? I think that's the key. It's just a bespoke type. No, yeah, it's just this type, right? Where what it contains is actually an int kind.I16, not just an int kind. And then this is the I8, this is the kind.I16, boom, there we go. Can't mismatch if you simply make a type from the value that you had, is the key insight there. And all of these are working. So what we have to do, let's do this. Let's do the sanity check test. And I know this isn't the fun part because we just did ints, but we're gonna do structs next time. So let's assert that type schema I8 is a unit. Assert failed at line 37. Hey, where'd you go? And that's line 37. Wow. There you go. And we're even going through our own generic function. So we caught that bug where this one doesn't count, basically. We can't just put T in the thing. Can we do one more type? Can we do an anonymous type of either yes, no, maybe, so with a string? Can I get a type schema for that? I think we should get a compiler error that we have not yet implemented in get type schema 13498. So and that is enum. I mean, can I show off my let me show off my error. Ice with span type schema for enum. So now this is what, oh, we got a bad span because it just happened here because that's the actual code. Oh well, that's fine. It's still a real span in our program. It says line 13. There it is. Okay. So looking towards next time. These have been simple, but we did get into payloads. So actually, it was a really good choice to get these working, to try and run this instead of, because it was really tempting to just go ahead and do struct enum or reference. But what will we do? It's pretty simple. We're going to have to recurse to make the schema for the types in each field. This function's already kind of set up to call itself nicely. We'll get static value IDs for each member. I think it should be pretty smooth. And then we get to think about fun types like lambda object. Oh, no, I guess there's nothing really to print. I was going to say let's print the type schema. But okay, well, thanks for watching.